Good morning. I think it would be better if we start the lesson and I can give you a little bit of time at the end to practice if you want to. Today we want to talk about geometry. Mostly I want to recap some ideas from what we have learned before. So it's not very formal. I want to introduce some concepts that probably you already know about them. The first thing that I want to start with, of course, the notion of a line, straight line. So let me write with different colors here. So a straight line. Yes, and then we have the notion of a ray, and then we have the notion of a line segment. Yes. So there are some terminologies I want you to know about them. So the straight line, you already know what does it mean. This is a straight line, I can call it L. The point is that it continues forever. Yes, and there is no starting point, there is no ending point. So that's a straight line. But when you talk about a ray, it means that you have a starting point, but you don't have any final points. Yes. So for example, if I talk about a ray, I start from a point, so let us call it A, and then I can draw this. This is a ray starting from A. So sometimes in some books you see this tip of the arrow to show that it starts from A and continues forever on that direction. For the line, sometimes you also see they put these arrows showing that these are going to infinity from both sides. So that is the notion of a straight line, that's the notion of the ray, and a line segment is just one piece of a straight line, which is bounded by 2 points from two ends. Yes? So if I have this and I have that, these 2 points, if I connect them with my ruler or whatever, what I get is a line segment. If I want to denote the line segment, I write AB. It doesn't matter if I write AB or BA. Both of them are representing this line segment. And in your book, I usually also prefer the method that the book is used. There is no difference between the length in writing, of course. From conceptual point of view, a line segment is a geometrical object. It's a shape. Yes? But for that, you can take your ruler and measure the length. It becomes a number. Yes? So in principle, there is a difference, of course, between an object and its length. There is a difference between Bobak and its height, yes, and his height, yes. So I mean, but in geometry, in this book, and I think it's a good convention, you need to interpret what you write from the context that you are looking at. For example, if I say the line segment AB, this AB is not referring to the length of AB, it is referring to this line segment itself. But if you see AB divided by BC, then of course you cannot interpret AB as the shape line segment AB and BC, because I don't know how to divide two line segments by each other, yes? Division is defined among numbers, not shapes. So if you see something like this, it means that AB is the length of line segment AB. But in some books, they want to be rigorous and strict, so they have introduced different symbols. For example, they sometimes put AB inside two parallel lines, and they say that whenever you see this in their book, this is the geometrical object AB, and when you see this symbol, it means this is the length of the line segment AB. But even though it is necessary to differentiate between these two, because they are totally different things, but in our book and in our way of writing, we don't do that, and it will come clear from the way that we are using it. Yes? Any questions? Okay. So these are the things that I want to know, and the next thing I want you to know is the angle. If I have two rays with the same starting point, for example, let me call this O, this part of the plane is called the angle between these two rays. And if I want to name them, so I can call this the angle O, But there is also a matter of confusion sometimes because, of course, I have colored this part when I say angle O. Somehow you think that I am talking about this. But of course you realize that there is another alternative here. Because when I have this angle, this one is also an angle. That's also some part of the plane between these two lines from that direction. So then it might be ambiguous when I say angle O, which one I mean. So there are some conventions that we can use. For example, I think the safest thing and the easiest way to do is to put some letter inside the angle that you're wanting. For example, I would write this alpha. And then I would, instead of referring to this angle as angle O, by the way, in the book you might see this symbol, or even, I don't know, in Swedish books they have written this in this form next to O. Okay, these are the same symbols. But I prefer to write alpha inside the angle and then talk about the angle alpha. I don't think there is a matter of confusion now here. Everyone knows that I am talking about this particular angle. Yes? But there is another one that I want you to know. So sometimes people put some letters on these rays and then they call this angle. That's also confusing. It's also ambiguous. People call it angle AOB. First of all, in this kind of way, in this way of naming the angle, you have to respect the vertex. By the way, this is called the vertex of the angle, and these are called the arms of the angle. Yes. So the vertex name should be in the middle. This you have to respect. But still, this is ambiguous. Yes. Because which one? Do you think angle AOB refers to this one or refers to the other one? Because, I mean, if you have worked with GeoGebra, you see that it is always confusing because that convention is correct. When you want to develop a computer program, you have to be very, very careful, okay, in defining your objects. So the convention should be something like this, because when I say AOB, it is still not clear I am talking about this or I am talking about this. Yes? To make it clear, we have this convention that, so what we do, if I mean this angle, so this is counterclockwise direction, okay? And this is clockwise direction. If I really mean angle alpha, okay, I have to start with BOA. Okay? So this means that always your conventional direction is counterclockwise. That is conventional. Okay? And when you say BOA, it means that I start with BO and rotate it so that I reach to OA. But this rotation should always take place in the counterclockwise direction. Okay? So if you see BOA, we don't need to be worried about these things at all. But I am telling you this because in case you are using GeoGebra, don't get confused. Okay, so when you say BOA, this BO is the starting arm, and you start rotating always by convention counterclockwise direction, or of course you can change your convention, but this is usually the case. I go counterclockwise direction and then reach to OA. And everyone agrees that for this one, I am actually traversing this angle. So if I write BOA, I am referring to this angle. But if I write AOB, what does it mean? I start from AO here, and I rotate counterclockwise again to reach to OB. So what happens? I start from here. I don't go in that direction because this is clockwise direction. I have to rotate again counterclockwise direction. So this means that I have to rotate this much to reach the OB. So in that case, this, if I accept this convention, this means that angle. This means this angle. Yes? But you really don't need to be worried about these things. I want you to know that. By the way, let us check GeoGebra if that is really the convention they are using. it's good to know about these things as well. I can also turn this off so you can see. No, that's one is better. Okay. So you realize that if you want to have an angle and if you want to call an angle in GeoGebra, you need 3 points. Okay, so let me just randomly put 3 points here. Okay, and now let me see. I want to have A as the vertex of my angle. So what should I do? I go to this feature here, angle, 3 points. You see 3 points. Okay, so now, what do you think? If I click on C first and A second, okay, always remember, if I want to make an angle at A, I have to put A in the middle, okay? So, if I choose C, then A, then B, which angle, if my convention is correct according to this, which angle do you expect, which will be clear? The smaller one or the bigger one? The smaller one. So let us check. I click on C first, and then on A, and then on B. So that's correct. Oh, unfortunately, this is in the radians. Forget about that. This is 1.2 radian. I will come back to this. I will try to fix it somehow. But for the time being, forget about the measure. So let me just get rid of it. So as I predicted, when I start from A and then from C and then A and then B, I realized this would be my angle. Okay. So now if I go back and now I click on B first and then on A and then on C, you see the other angle is now shown. So this is the way that they don't get confused if you want to use this software. And that is actually correct, because I hope that you agree, even if I write A or B without any conventions, it is not clear I'm referring to the small one or I'm referring to the larger one. You can have another convention. You can say that, okay, whenever I call this one, I mean the smaller one. Well, I mean, it's important to understand that this is the difference. So if you really want, using this convention, you can rule out all ambiguities. If you have this convention, when I write angle OAB and I tell you that I am using that convention, everyone knows about which angle I am talking about. There is no matter of confusion. Yes? Okay, so at least you understand this, but then I probably should be able to change this into somehow. Let me go. This is GeoGebra number 5. Yes, I will go to GeoGebra number 6 then. It's easier for me. Okay, let me just stop here. Now. So this is the first thing about angles. And then the unit of measuring angles which you learn is degrees, is the degree unit. And what does it mean? So if I want to give you a feeling about what is a degree, it means that assume that you have a circle, and then you start partitioning the circumference, the circle itself, into equal parts. How many equal parts? 360 parts. If you do that and take any 2 consecutive points, of course I am a little bit exaggerating, because if I just take this, I will not be able to fit 360 pieces in this circle, so it should be a little bit smaller. But if I exaggerate this, what I'm meaning, you take 2 consecutive points and then connect 2 consecutive points to the center of your circle. Then, in that case, you get an angle. This angle is called 1 degree with the symbol that this is degree Celsius. Okay, so that is just 1 degree. Okay, so that is the meaning of 1 degree angle. So when I say that this angle is 30 degrees, it means that I can fit 30 of those angles side by side inside this angle. Yes, so that's the meaning of 1 degree. Okay, so what else about angles? Well, we can have different angles, yes. So might be the famous one is that I have a straight line, yes, and then I just pick a point on it and I call it O. And then I have this angle. That is called a straight angle. Okay, so what is the measure of the straight angle? Everyone knows about it. What is that? 180 degrees. So that is the measure or size of a straight angle. So that's a straight angle. I can have a right angle, yes? So this is the meaning of a right angle. So this means that the measure between these two sides is 90 degrees. So that is called a right angle. Okay, there are some other terminologies I want you to know. One of them is called an acute angle. And then another one is obtuse angle. So I'm just telling you because I want you to know these English words for these. So what is the meaning of an acute angle? An acute angle is an angle. Yes, do you want to say? Yeah.
Below 90 degrees.
Pardon?
Below 90 degrees.
Below, between 0 and 90. Be careful. 0 is excluded. 90 is also excluded. So when I say that my angle is acute angle, let me consider theta. That's a very famous Greek letter for measuring angle, for naming angles. So theta is strictly greater than 0 degrees and is strictly less than 90 degrees. That is called an acute angle. Okay, and then if theta is strictly larger than 90 but less than 180 degrees, that is called an obtuse angle. Okay, but then we also have another concept related to an angle that is called the angle bisector, the bisector of the angle. And what is that? The bisector of any angle is the ray which starts at the same vertex, okay, and goes inside the angle, but bisects the angle into two equal pieces. Yes? So this is called an angle bisector. So if assume that if this angle is beta, if this angle is gamma, then beta and gamma are exactly equal. If this is going to happen, this blue line is called the angle bisector of the angle alpha. But that is also something about the angles I want you to know. Okay, so I don't know. So you can immediately understand these things. You really, because you have a strong intuition about this kind of geometry that we have. So for example, if this angle is alpha, this angle is beta, what is the sum of alpha and beta? Is 180 degrees. If two angles add up to 180 degrees, we say they are supplementary. Yes? So alpha and beta are called supplementary angles. For example, if I tell you, I don't know, 120 degrees and 60 degrees, this is a pair of supplementary angles. Why? Because they add up to 180 degrees. And if they add up to 90 degrees, they are called complementary angles. Okay? So if alpha, so complementary, is they add up to 90 degrees. For example, 75 degrees and 15 degrees. They are complementary angles because they add up to 90 degrees. Another thing that I want you to know is the notion of the vertical angles. I don't know if you have heard the word vertical, or sometimes I have heard the right opposite. But I think the vertical one is the best one. So opposite angles. So what do we mean by vertical or opposite angles? So it means that if you have two straight lines that intersect each other at some point, then these two angles that are opposite each other is called the opposite angles or vertical angles. So this means that this angle alpha, beta, gamma, and theta. Alpha and beta are a pair of vertical angles. Gamma and theta is also a pair of vertical angles. So you know what is the meaning of a vertical angle, yes? But there is a very nice theorem. Theorem in geometry appears a lot. Of course, in mathematics, this word theorem means a statement which is always true. Yes? A statement which is always true, and it is useful for proving other statements, is usually phrased or coined with the name theorem. So one important, very important theorem is that any pair of vertical angles are equal in size. So that is more or less intuitively clear for you, but let us see why. So alpha, so I am claiming that if I draw two intersecting lines, then alpha is equal to beta always, and gamma is equal to theta always. So it means that you can phrase it in this way. Any pair of vertical angles have equal sizes or equal measures. Sometimes instead of saying the size of an angle, people call it the measure of the angle. Okay, so let us understand why alpha is equal to beta. Of course, one way is to take your protractor and measure this one and that one and say that, okay, they are equal. But this is not good, because in mathematics, when we say they are equal, we mean they are 100% equal without any kind of error at all. So if you take your protractor, you cannot measure the exact value of alpha, because when you do measurement, there are some errors involved in any measurement. If you have a a very precise tool, even for example, assume that you have a protractor using laser beams to measure angles. But even in that case, you cannot measure the exact value of this one. So experimentally, if you want to understand that, of course, you cannot make sure that they are really equal. So they might be equal until the 10th digit decimal points, but the 11th digit they differ. Okay, so you cannot measure that. Of course, even if your technology becomes more advanced and you can measure that, but what happens for the 100th decimal point after what happens for the 100th decimal point? So this means that mathematically we have to have an argument to show that alpha is always equal to beta without any errors, 100% correct, yes? So one way we can do this, so my goal is to show that alpha is equal to beta. So this is my question mark. But I would involve gamma in the problem, okay? So I would say that one thing I'm sure about, if you tell me what is alpha plus gamma, even without any measurements, I am sure what is the answer to alpha plus beta, 100% precise. What is the answer?
180.
That's 180 degrees, because if I add alpha to gamma, it makes a straight angle for me. And then if I ask you what is beta plus gamma, if you tell me do I know gamma, do I know alpha, do I know beta, I don't know. But I know 100% that alpha plus gamma is 180 and beta plus gamma is also 180 degrees. And I know that if two numbers are equal to the same number, they have to be equal themselves. So alpha plus gamma is equal to beta plus gamma. Yes? And then what happens, I can add minus gamma to both sides. When I add minus gamma here, gamma is cancelled, alpha is left. When I add minus alpha here, gamma is left. Sorry, if I add minus gamma here, beta is left. So you see that alpha is equal to beta. This very simple argument shows that alpha is always equal to beta, regardless of how they are actually intersecting and what is the size. Yes. So I want you to. So in the exam, you don't need to prove this unless I am asking you to prove exactly this idea. Otherwise, you can just simply use that. Okay, that's the point. Okay. Another thing is, let us talk a little bit about this very important theorem. Or sometimes, by the way, in any subject there are statements that we cannot prove. Okay, so here this theorem was this statement: alpha is equal to beta. And this method that I showed here is my argument. That is called the proof. So I was able to prove this to you using these ideas. So I had a proof. But this is not always the case that I can prove any statement in the subject that I am studying. There are some statements that I accept their truth and try to explore the consequences of those acceptances. Okay? Those are called axioms or postulates, yes? So if I ask you what is the meaning of an axiom and how it compares to a theorem is a statement. A statement is a declarative sentence, full stop, yes? Axiom is also a declarative sentence. But for a theorem, I can present a proof based on the previous theorems or the things that I have admitted to be correct. But axiom is something that I accept to be correct without being able to present a proof. Okay, so that's called an axiom or a postulate. Of course, the number of statements that I accept without any proof should be as low as possible. And I would try to probably find the proof for other statements that I am telling. So one of those axioms is parallel axiom. Okay? It seems obvious. It is not in direct contradiction with my intuition about the universe that I am living. But we don't know any, so we don't bring any proof for that. We just accept it and try to explore its consequences. If I accept this one, let us explore what happens. So this parallel axiom tells you that if I give you a straight line, L, and if I give you a point which does not lie on the line, then you can draw a line from A, which is parallel to L, and that line is unique. Yes? So it's claiming too much, but without proof. Intuitively, you feel that this is correct. So this means that when I take this point, I can draw a line which is parallel to L. So let me call it L prime. So L prime is parallel. This is the symbol that I use for parallelness. L prime is parallel to L, and it passes through the point A. And if I wait, someone else do the same job, they will get the same line. So it means this line is unique. No one can draw another line that is parallel to L and is passing through the point A. Okay? I hope that it is intuitively it is correct. Because if I want to draw another line that passes through here, I have to, if I want to make a distinction from that line to my line, of course I will lose the parallelness. So somehow intuitively it's correct, but we accept it without any proof. So that is the parallel axiom. It's a very simple intuitive idea. If you give me a point outside a line, I can draw a line through A parallel to L, but that line is also unique. So it claims two things: existence of such a line and uniqueness of such a line. Okay, another by the way, you know what is the meaning of parallel, yes? They lie on, by the way, that's also good to know, because these two lines, if I continue them, they will not intersect. But do you feel that this is a good way to say that these two lines are parallel? So they are not parallel. They don't intersect in a space, yes? But they continue forever from these directions and these directions, but they don't intersect. But you feel that they are not parallel, yes? So two lines that are parallel, they have to be on the same plane, yes? So here, this orange one lies on the plane of this table, but this one, for example, lies on my hand. They are not on the same, even though they are not intersecting, but they are not lying on the same plane. But these two lines are lying on the same plane. Which plane? The plane of the whiteboard. So they are on the plane of the whiteboard and they do not intersect. So we say that they are parallel. These two lines are called skew parallel. Yes, if you want to learn the word, skew parallel. Two lines that don't intersect, but they don't lie on the same plane, are called skew parallel. Okay, these kind of lines. Okay, so another axiom that this is important, and I want to start solving some problems for you here, is this one. So if I have two parallel lines, and by the way, if I want to show these lines are parallel, I put this symbol on both of them. So assume that L1 and L2 are parallel. And then another line that cuts both of them. This is called a transversal. So these words, there are many words that I introduced. I wanted to learn all of them. So a transversal is a line that cuts two parallel lines. Yes? Okay, and then this angle here that you see, let me call it alpha, and this angle here you see, let me call it beta, these are called corresponding angles. Okay? So corresponding angles. What do you feel about the sizes of these two corresponding triangles, corresponding angles?
They should be equal.
They feel to be equal. That's one of those axioms that we accept here. We accept that. So this is called a correspondence angle axiom. Corresponding angles axiom. So when I write axiom, you don't expect me to give you a proof. You might, of course, discuss why this is true in the first place. It's like, you know, for example, consider the chess, the rules for the chess. So I tell you that if you want to play this game, the queen moves like this, the rook moves like that. You cannot say why. Yes? This is the rule of the game. And then later, if you accept these rules, you can enjoy the game, or you can explore the consequences of these rules for that particular game. Yes? Mathematics is also the same. You cannot prove everything. You have to set up some rules, the minimum number of rules, and then try to explore what happens if I accept that these rules are true. Let us see what happens, of course. And that's more or less the same thing. But of course, mathematics has proven itself to be very, very fruitful. So rather than chess, yes. So it means that that's more or less comparable to any game, for example, the chess. Okay, so alpha and beta are corresponding angles, and they are the same size. They have the same sizes. Alpha is equal to beta. But if we accept this one, then you see that I will have 8 angles actually. 4 angles are here, 1, 2, 3, 4, and 4 angles here, 1, 2, 3, 4 here. Okay, so let me name them. So alpha, beta, this angle, gamma, theta, I don't know, let me just use Greek letters, rho, and lambda, for example. I don't know, this is xi, and this is nu, for example. Yes? Okay, might be xi is harder. Let me just write sigma. It's easier to write. By the way, that's also good. Tau. Yes? That's tau is also good. Okay, so you see that I have 8 angles involved, but angle beta and angle tau are of the same sizes. Why? Because this is, what was the name? They are vertical angles. They are opposite angles. So they are the same size. This is also the same. Lambda and nu are of the same sizes. This one and that one are the same sizes. This one and that one are the same sizes. But why, for example, alpha and tau are of the same size? Yes?
Because alpha and theta
Yes?
are vertical angles.
So alpha and theta are equal, yes?
And theta and what was the name?
This one?
Yes.
Tau.
Tau are transversal. Transversal.
They are corresponding.
Oh yeah, that's what.
So they are corresponding angles. They are also the same. Yes, so you can say like this. You can say that alpha and beta are the same. Why? Because of corresponding angles axiom. Okay? But on the other hand, alpha itself is equal to theta because they are vertical. And tau is equal to beta for the same reason. They are vertical. So theta is equal to alpha, tau is equal to beta, but I know alpha and beta are equal, so it means that these two have to be equal themselves. So this means that if I have a transversal line cutting two parallel lines, I get 8 angles, 4 here and 4 here. All acute ones are equal, and all obtuse ones are also equal. Yes? So remember, whenever I have a transversal cutting two parallel lines, all the acute angles are equal, not only the ones that are vertical. No, you can take alpha with theta, with tau, sorry. Okay, and all the obtuse angles are also equal. So remember this picture. Alpha is equal to theta, beta is equal to tau. There is nothing new. They are vertical, but this equality is something new. Yes? And then the same story here. Gamma and rho are equal, nothing new, they are vertical. And then lambda and nu are also equal, nothing new, they are vertical angles. But this one is also equal to this one, is something new. So I want you to have this picture in mind. Okay, and then of course there is one special case. The special case is that I have two parallel lines and then the transversal cut them, but it is perpendicular. Okay, then all these 8 angles are 90 degrees. So in that case, all of them are equal. But that is also trivial. Okay? For example, let me try to solve some problems here. Okay, by the way, let me also talk about this. So what is this? What is how alpha is related to lambda? How alpha is related to lambda? Yes?
If you add those two, you'll get 180
8.
degrees.
They are supplementary, yes? Because alpha is equal to beta, but theta plus lambda is 180, so it means alpha plus lambda is also 180. So these are something that you can immediately explore yourself. So for example, let me just draw some pictures and I ask you to these simple examples, I think they're really boring. Let me just do a little bit better ones. Okay, so for example, I have this figure. I don't think, of course, this one is also hard, but something like this. This line is parallel to that line. and this angle is given to be 40 degrees, and this angle is given to be 60 degrees. Yes? My question is that how much is this angle, which I call it x? So these two lines are parallel. Yeah, this is a line that makes an angle 40, this is a line that makes angle 60. Then of course these two lines also make an angle here. My question is that what that angle is. How much is that angle? Yes?
260.
I don't know. Let us see. How did you calculate?
I draw a line.
Exactly. So from here, you draw a line. What type of line?
A parallel line.
Parallel line to these two. So this is what she has done herself. So in principle, in geometry, if you do something like this, you have to explain some words. So you say that I draw a line parallel to these two. So you have to express it somehow. Okay. And then what?
And then I took the
Don't forget about it. Don't worry about the name for the time being. Okay. So this is a line that you draw.
yes.
Okay. And if you want to compare it with that picture, it is also instructive if I, in my head, continue these. And that is called this theorem, yes? Corresponding angles axiom or whatever. So you want to use that theorem 2 times.
Yes.
I think so. Okay, one for this pair of parallel lines. This is playing the role of your transversal.
Yes.
But then I will take this pair as my parallel lines. This time this will play the role of my transversal. So this means that in your head, probably you are doing this. You take x into this part, so let me call it x1. Another part is this one, let me call it x2. It is clear that if I can find x1 and x2 separately, then I can add them and I can get the whole x. Yes? Okay. So now I want to hear from you. For example, can you tell me what is x1?
I did it another way.
Okay.
I used 40
Yes?
and made a new angle
Here?
opposite. Yes.
Yes. Okay, so that's also another way. So what you are saying is that this is parallel to this. This is transversal. So if this is 40, this angle is also 40. Yes, that's correct. Okay, and then you repeat the process for this one. Yes? So you would say that this one and that one are parallel. And this one is transversal. If this is 60, this angle should also be 60. And then, of course, when you add these two together, it becomes 40 degrees plus 60 degrees, which is 100. But the question is the opposite angle, is that angle. But I know the whole angle is how much? 360 degrees. So the x that I am looking for is 360 degrees, which is the total full circle, minus this 100 degrees. So the answer is, as you mentioned, 260. Yes? So that's correct. Okay, let me draw another one for you here. So this is the picture, if I can draw it correctly. So here, this is my line. I have another line here, another line here. So they have put this arrow here, here, and there. So this means these three are parallel. And they have given you this angle is 50 degrees, and this narrow angle here is 20 degrees. And they are asking for you about this angle. What is this angle?
I got x is equals to 150 degrees.
I don't know, but you need to tell me how to do that. I haven't calculated yet. Yes?
So if we just focus on the Z shape, we can see
Here,
that
this Z shape.
yes,
Okay.
we can see that that's a transversal.
Yes, so
line.
that's a good idea. So if you have this Z shape, it means this angle is always equal to this one. Of course, you can also talk about this N shape or the other way around, which is, I don't know, another letter. Okay, so all these angles are equal, yes? Okay, so what you are saying is that if this line is parallel to this one, and this is playing the role of the transversal, if this is 50, the total angle here is also 50. Yes? So then what is left for this part?
30 degrees.
It is 30 degrees, yes.
And then we can focus on the lower two parallel lines.
Yes, these
Yes.
ones,
And
okay?
that line is then the transversal line.
Yes, yes.
So
So where is your Z shape? It is not, it is a little bit hidden, so you can extend this, and then you have your Z shape here again. Yes? And if this is 30, what happens to this?
that's also
That's also 30. And if this is 30, what is the angle that I want to calculate? Is the supplement of 30, which is, as you mentioned correctly, 150. Yes?
I just did it a bit differently.
Yes, maybe you can share it with us.
So I drew the three parallel lines.
So, yeah, you mean you mean extending them, yes?
Yeah.
Okay, so we extend them.
The 50 degrees, using the corresponding angles,
Yes.
I moved it as in the Z shape to the yes, there.
Here, that's also 50.
I know.
Then I used the vertical angle
With this one,
to do this
We're still on the
outside.
same.
Yes,
this one,
yes,
that's also 50.
yes. And then I calculated it to be 180. So I did 180 minus 50 becomes 130.
Yes?
130 plus 20 means the last angle is 30, and then just
Yes, that's also correct. That's also correct. Okay, so I want to stop here, but this part is not finalized yet because I want to give you a little bit of time, as I promised, to practice yourself. But we will come. I haven't finished this first part. I will come back to it again next session on Thursday. Okay? But for the time being, I think it's better to go back and start working on the problems as they were supposed to. Any questions? Thank you.